Okay, folks, before I start with Chapter 2, just a few things about the test you wrote, the semester test. There were apparently a few problems with a few questions, not many, where the question, the actual mathematical typing did not show. I will deal with it in the best possible way, so don't worry about that. I will make sure that I've got 2 screenshots from students showing me those questions. So yeah, you will not be disadvantaged. I promise you that. I will make sure. I went through all those questions before the test and they all showed perfectly. I did the test 4 times just to make sure everything is fine, but it seems like there's always gremlins that slip in. Okay, as promised, sorry for this taking so long. As promised, your supporting videos for the sequence chapter. Now, what you see on the sequence chapter here is a nice exercise to do. The Tower of Hanoi. Okay, this is what this whole puzzle is all about. If you don't know about the Tower of Hanoi, it's a very, very, very interesting exercise to do. So I would suggest just do it for the fun of it. You will always learn something from it, and you can use it one day when you teach as well. I want to start with immediately with focusing and zooming in on our, oops, there again, the wrong pen, our description of sequences. Now you can see there's another small activity for you to do over here. If you want to pause the video and try and do this activity from the book, you're welcome. By the way, we're on page 136. So what is a sequence? A sequence is simply an ordered list of numbers, and the key word here is that word ordered, list of numbers. For example, we can look at a sequence here. They say, where's my, there we go. We can go to a sequence 0, 1, 2, 3, 4, 5, and we'll see that these are the natural numbers. That's how we started, that we learn counting. So that's how things appear in nature, 0, 1, 2, 3, 4, 5. Okay, this is different from the set, the natural number set, because while the sequence is complete, list of every element in the set of natural numbers, in the sequence we must very much care what order the numbers come in. So for this reason, very important, we have used variables to represent terms in a sequence, and those would look like that. Folks, you are used to working with Tn, T1, T2, T3. In Oscar Levin's book, our textbook, we use this notation. So to refer to the entire sequence at once, we will write an, where n is natural, or we will write an, where, so that's how we're going to refer to sequences. The entire sequence is given by that, or sometimes, if we are sloppy, we sometimes just use an, in which case we assume that we start at a naught. Okay, so that's different from what you did at school level when you did sequences. At school, when you wrote Tn is equal to 2n plus 1, we didn't start at T0, we started at T1. We could have started at T0 if we wanted to, but that was just your experience so far. So we might replace the A with another letter that we're saying here. Okay, we can replace the A with another letter, and then sometimes we omit a naught, as I said now, and start at A1. In which case, we could use an, which indicates that n is bigger and equal to 1, to refer to the sequence as a whole. So the number of subscripts here, the number in the subscripts is called the indices, or the plural for indices is index. So if we talk about A2, The 2 is the index of the term, and A represents the sequence that we're working with. Okay, so A2 will be equivalent to what you've used at school as term 2, and maybe in other possible courses as well. Okay, so it's important that we know that. Why is it important? Because that is the notation that we're going to use in this chapter. And you must know what we're talking about when we use the notation. Now here specifically, the sequence, oh, again, the wrong choice. Let me go back. Specifically, the sequence an, where n is bigger than or equal to 1, is a function with domain n, where an is the image of the natural number n. So what this is referring to is usually when we talk about functions, we talk about f of x, and then we have various coordinate pairs x, y that tells us the relationship between the coordinates via the rule f of x. So all we're saying here is this is n and an. So an is determined by the value of n. Okay, so the one is the image, the other one is the image which belongs in the domain, and the other one is in the codomain, if you want to think about it in terms of the previous chapter. Okay, so let us see. I'm just going to get rid of this because I think I need as much space as possible. Let us see where, let me get rid of that as well. Sorry. Let us just get rid of that. There we go. Now we've got enough space. Okay, so can you find the next term in the following sequence? Let's quickly talk about the 7, 7, 7, 7. Well, we know that this is a constant sequence. There is no change in the numbers, so it is 7, the next term. For the very next sequence, we have 3 minus 3. Then we have 3 again, then we have minus 3. Look at what I'm writing. I say minus 3 and I write minus 4. Okay, so minus 3 and then 3, so the next term will be minus 3 and 3. So what's important to notice is that these terms alternate in sign. So if you were to add them and work with a series, you'll most probably end up with either 3 minus 3 or 0, depending on where you stopped your sequence. Okay, for sequence number 3, let's have a look at the regularity here. 1, then 5, then 2, then 10, oh my goodness, then 3, then 15. Now you will see if you try and analyze this sequence, there's a difference of 4, here's a difference of minus 3, there's a difference of plus 8, here's a difference of minus 7, there's a difference of 12. So insofar as the usual way that we think about regularity and what changes and not, that is throwing the cat amongst the pigeons. So there must be something else that's happening here. So let's just stand back from that sequence and zoom out. If we zoom out, we'll see that there's a difference there. The difference goes to 3. And then there's a difference to get from 5 to 10 and 5 to 15. And if we want to write this difference down, let me do the red one first. We can see that's a positive 3. That's a positive 1 to get to from 1 to 2. To get from 2 to 3 is another positive 1. If I look at the 5s, I get 1 5. Then I can either add the 5. I either am adding 5 here and adding 5 there, or I am multiplying by 2. Now let's see if that is indeed the case. From 5 to 10, yes, I can multiply by 2, and yes, I can multiply or add 5. But if I want to get from 10 to 15, I can't multiply by 2 because 10 times 2 is 20. So it then cuts out the times by 2, and I can see that I'm adding to get to the next term. So the very next term will come from the 3. So I'll add a 1, and that will be a 4. And the term after that, I'll add, so there I added a 1. Here I will add a 5, and we will then only get the 20. So can you find the next term in the sequence as we've looked at the first 3? If we look at number 4, I'm just going to draw an arrow there. We can see clearly to get from 1 to 2 to 4 to 8 to 16, I think it's quite obvious. We just multiply by 2 to get from one term to the next. So that's the sequence where things will be doubling. Look at me. I think I should have stayed in bed this morning. That's a times 2, and that's a times 2. Okay, let's look at the next one. The next one is quite strange. It's got 1, 4, 9, 16, 25, and 36. Now, I can hear some of you saying, oh, please, it's not difficult. This is the sequence of squared numbers. Okay, but let's say we didn't see that. Let's just assume that Duplessis is stupid. Duplessis has never done this type of work. Then we would say, oh, okay, from there to there we add 3. There to there we add 5. There to there we add 7. From there to there, look at the beauty here. We add 9, and then we add 11. And then we can see that in the second difference, we have a growth of 2. So the growth on top of the growth will be 2. So somebody like Tandazile will see immediately that this sequence has a general term n squared, where n is bigger and equal to 1. Okay, so she would say that in general terms, let me make a little bit of space here. In general terms, she would then say that not even going to undo that. an is equal to n squared, where n is greater and equal to 1, and she'll be 100% correct. Now, Duplessis, which is now still battling to try and see the pattern here, would then go and say, oh, okay, if this is the pattern 1, 4, 9, 16, 25, and what is it, 36, I saw that I add 3, I add 5, I add 7, I add, 9, I add 11, and then I add 2, and I have a second difference that is constant, which confirms what Tandazile saw. She saw it is a squared number. Okay, so let's see how Duplessis would have gone ahead. Duplessis would have then said, okay, let me go and find the 0 term. So Duplessis would say Tn is equal to an squared plus bn plus c, identifying that this is quadratic and that the a value is 2, so that the second difference rather is 2. So immediately the a will become 2 divided by 2, which is 1, plus bn, and now I'm going to try and find the c. So I go back. So if I take 2 away here, then I am at 1. And if I take 1 and I take it away, I get 0. So in other words, I take a further 2 backwards. I get to 1. 1 minus 1 is 0. So my c value, my constant, I just found to be 0 over here. Now the only thing that's left is b. So I go back to term 1 and I say, okay, term 1 was equal to 1. So that means that 1 is equal to 1 plus b, which makes b 0. And finally, I can see that Tn is n squared. And then after that, I will feel so stupid because I just saw that it is the squared set of numbers. Okay, so you've got to be awake, folks. What I'm trying to show you here is you have to have a sort of a concept image in your head. If you look at a sequence of numbers, this is more or less, if I look at the difference, do they double, do they half, what is happening here? Am I adding, am I subtracting? And then just From now on, we won't be using that. We'll be saying AN. So this will be AN, that will be A1, and this will again be AN. Now let me try and see if this will erase. So I can make, or let's just make space for number 6 down here. Number 6 is quite interesting. Number 6 is 1, 2, 3, 5, 8, 13. And I'm going to need space here, so I'm just going to get rid of that. 13 and 21. Now let's see. To get from here to here, I add 1, then I add 1, then I add 2, then I add 3. Now this is interesting. Then I add 5, and then I go and I add 8. So what am I working with? I'm working with a sequence that grows in the same way as Fibonacci sequence. Just look at this. Remember Fibonacci said 1 plus 1 makes the next one 2. 1 plus 2 makes the next term, which is 3. 2 plus 3 makes the next term, which is 5. 5 plus 3 makes the next term, which is 8. So this is very, very interesting. So it seems to be the Fibonacci sequence that has sort of shifted. Let's look at how we can express this as a sequence where we absolutely work with the difference as the Fibonacci difference. So can we write this? This is the big question. How do we write this? Do we write this in this form? Or is there another form that we can write this in? And we're going to get back to this part just now. We're going to express this as a recursive sequence. Okay, and that's coming up next. Okay, so let's leave that for now. We'll come back to that later. Now you can see the growth here is 0. The growth there is 1, 1, 2, and 3 again. Okay, let's look at the next sequence, which is sequence 7. Now that one's easy to see. I'm sure you guys recognize that as your triangular number. So we're not even going to look at that one. Remember, it's a growth of 2, then 3, then 4, then 5, then 6, if it's triangular. If we look at the next one, number 8, it says it's 2, 3, 5, 7, 11, 13. And if we try and understand what's going on here, add 1, add 2, add 2, add 4. And then from 11 to 13, you add 2 again. So it's rather strange what's happening here. We don't know what's happening in that sequence. And we don't have enough information to find out what it is that's going on for number 8. For number 9, let me get rid of that. For sequence number 9, we can see it's a growth element of -1. To get from 3 to 2, we subtract 1. To get from 2 to 1, we subtract 1. To get from 1 to 0, we subtract 1. And then 0 to -1, we subtract 1. So that is basically showing you that these differences can also be negative. And then again, we hit a funny one there. Look at that. 1, 1, 2, 6. No difference. 1 difference. 4 differences. And you don't know how it continues. So even though, folks, we've made certain predictions on how these sequences are going to grow, we cannot say for certain that is what's going to happen. We absolutely need more. We need more about the structure of the sequence, how it works, and what sort of happens next. Okay, so let us have a look. Here we could have said, here we times by 1. I just caught that. We could times by 1, times by 2, times by 3 to get to 6, and then the next one will be times by 4, which get to 24. But the fact of the matter is that this next could be 0, then again 1, then again 4. So you'll have, the numbers you'll have in that case will be 6, 7, 11. And then again 0, we don't know. We have too little information. That's the point. Okay, so in fact, those next terms in the sequences that we were predicting were just that. They were predictions. They can't be seen as 100% accurate. Okay, so let's have a look. We now get into the nice theoretical stuff related to sequences. First of all, given that no number of initial terms in a sequence is enough to say for certain what sequence we are dealing with, we need to find another ways to specify a sequence. We will consider two ways. We will consider the closed formula and we will consider the recursive definition. Now, if we talk about the closed formula, then we are referring to something that you are used to working with. You are used to working with things that look like that, 2n plus 3. And remember, what did we say? In this course, we don't work with tn. We're going to say an is 2n plus 3. Now, folks, that is a closed formula. So the pure definition for that is a closed formula for a sequence. An is a formula for an using a fixed finite number of operations on n. This is what you normally think of as a formula in n, just as you were defining a function in terms of n. If you look at that, that's nothing more. Its equivalent in function language will definitely be y is equal to 2x plus 3. It's the same thing. The structure of the sequence is given by that generalized version of what we saw seeing. Let's talk about a recursive definition. Now, the recursive definition, sometimes called the inductive definition for a sequence an, consists of a recurrence relation. Now, what is a recurrence relation, we can ask ourselves? Well, it is an equation relating a term of a sequence to the previous term. That is what it does. Okay, I'm going to try and underline that the way as accurately. It's a term of the sequence given in terms of the previous terms. But what do we need? We need an initial condition. A list of a few terms of the sequence, one less than the number of the terms in the recurrence relationship. Okay, so we need an initial condition. Now, sorry, that initial condition can be term 0, term 1, it can be term 5. If you have term 10, you can access term 11. That's what the recursive definitions are all about. So what is a perfect example of a recurrence definition? The next term is twice the previous term minus 3. But now you can see you need to know where the sequence starts. So we can either tell you that T0, oh sorry, not T0, I'm going to make that error, it's not really an error, but it's an oversight. An or A0 in this case is equal to 3. Okay, so if A0 is equal to 3, that's the recurrence relation, and we're working with natural numbers, then we can say, oh, okay, if A0 is 3, then n plus 1 is 0 plus 1, so A1 is equal to 2 times the previous one is A0 minus 3. So that gives me 2 times 3 minus 3, and the sequence kicks off at 3. The next term, A2, will be twice the previous term minus 3. So that will be twice a1 minus 3, and a1 was 3. So again, we have 3. Okay, let's just check ourselves. 2 minus, yeah, that's correct. Okay, so the next term is twice the previous term, minus 3. The next term in a sequence will be twice the previous term, which was a2, minus 3. So twice 3 minus 3 brings me back to 3. So that's how my sequence, what the sequence more or less looks like. So if I go for any term in the sequence, I need to know the preceding terms. In this one we don't, because it works out to be a constant sequence. Okay, but in others that we're going to work with, we're going to see. So how do I get to an minus 2, for instance? Well, according to the rule, it is the previous term, which is an minus 1. Now, folks, please note that these are subscripts. They're not in the power, and they don't stand next to the number. Okay, so it's twice the previous term minus 3. And then again, you obviously have an initial condition that's been given to you. Okay, so let us see how this is going to work. Here are some closed formulas. So a closed formula is a formula that gives you the general term. Now, if anybody were to ask, what's the difference between a closed formula? What's the advantage of a closed formula, rather? The advantage is access of a closed formula is access. I can get to term, there I go again. I can get to term 102 if I have the closed formula. So that will be 102 squared, according to that rule. According to the next rule, A102 is equal to 102 times, now let me just get rid of that. I don't think it's going to erase. So let me get this out of the way quickly, then we go back. So multiplied by, if we look at the formula over here, n plus 1, so 103, divided by 2. And that's calculator work from there onwards. The same for this thing, it looks so complicated, this one. We simply just plug the n into the equation. Whereas if I have, let's look at this. Let's look at an, which is equal to 2, an minus 1. Okay, and a naught is given as 27. So they've given us the initial condition. If I want to find a 10, I must get a 11. If I want to find a 11 or a 9, I need to find a way to incorporate that. And that is starting at a naught. So I can start at a1 and say it's twice a naught. So a2 will be the previous term, which is that, times by 2, according to our recursive definition. The next term will be 2 times a2, whatever a2 was. And I need to do that until I get to a10. So I need to find all of these term values before I can get to term number 10. And that is what makes a recursive definition so difficult to work with. In some sequences, it helps. In others, it just creates unnecessary roadblocks or obstructions, if you wish, for a lack of a better word. So now you might wonder why we would bother with recursive definitions for sequences. After all, it is harder to find the nth term in a recursive definition than in a closed formula. Now that's going to become very important later. This is true, it says, but also harder to find a closed formula for a sequence that is to find a recursive definition that is defined by a recursive definition. So it's harder to find the closed formula for a sequence than what it is to find the recursive definition. But also the other way around is hard. If you have something that you cannot just it's impossible to write a closed definition for, then that's why we default mode then into recursion. So to use a useful closed formula, we might first find that the recursive definition, then use that to find the closed formula. This is not to say that recursive definitions aren't useful for finding an. That is very important. We're not saying it's not useful. We're actually going to find a way to work with that. So you can always calculate an. Given the recursive definition, it might just take a while. Now let's have a look. The example. They say to us, they want a 6. Okay? And the definition is an, which is 2n minus 1 minus an minus 2, with the initial condition 3, a0 is 3, and a1 is 4. Now let's just stand still there and see, why did they give us 2 initial conditions? Why this and that? Well, the answer lies in the way the function has been defined. You need 2 prior terms to get to a particular term. You need 2 prior terms. So if I now want to find term 2, I can say, oh, okay, it's term 1 twice. Is that an n? Yeah, there's an a missing there. It's twice an. So twice term 1 minus term 2, which was, or the term in front of term 1, which is a0. So this gives us 2 times 4 minus 3. 8 minus 3 is 5. So a3 will then be twice a2 minus a1. a1 we have, that's 4, and this is twice 5, which gives us a3, and therefore a3 will be 10 minus 4, which gives us a beautiful answer of 6. Okay, and we continue with that. We can continue with that and build the sequence. Okay, now let's see. There's the first 6 terms obtained from the recursive definition. We've got, I'm going to change color, we've got a0, we have a1, we have a2, a3, a4, a5, and a6. I just didn't go all the way, but I'm going to write these terms down so we can see if we can notice something. 3, 4, 5, 6, 7, 8, 9. Now look at that. Look at the poetry here. There is the way the sequence grows. Now we would have never seen it if we just looked at that particular way that the recursion was defined. This might have been a little bit of a hint, we don't know, unless we've worked out at least 5 or 6. So now you can see what the closed formula would be. If we look at an here, an, when n is 0, is going to be n, okay, plus 3. Let's see. a1 will be 1 plus 3. a2 will be 2 plus 3. a3 will be 3 plus 3. So we've worked from the recursive definition which was given there to a closed formula over here to express our sequence in. Okay, so sometimes it's difficult, sometimes it's not. Okay, so you just literally have to work slowly and see can you get there. So this is not quite enough though. That's the sad news. It's not enough. Since there can be multiple closed formulas that satisfies the same recurrence relationship. Okay? We must also check, and this is very important, we must also check that the closed formula agrees with the initial conditions of the recursive sequence as it was defined. Now remember, our closed formula was an is equal to n plus 3. Now let's see, does it work for a naught? Is it going to be 3? And the rule is definitely. Does it work for a1? Well, a1 was 4, and 1 plus 3 is indeed 4. So it works for the initial conditions. Since it works for them, we can now conclude that we have the correct closed formula. So the key word here is check. Check if you are on the same page as what is expected for you in terms of closed and recursive formulas. Okay, very important paragraph over here. They say, one useful method is to relate a given sequence to another sequence for which we already have the closed formula. Now, folks, that is important. One way to do this is to relate. Now, you saw me on the previous pages. I said there's a triangular number. Okay, and the triangular number was 1, 3, 6, 10, 15, 21. And immediately I said, we're not even going to look at that. So if you get something that is 2, 4, 7, 11, 16, 22, folks, this is what this sentence means, for which we already know the closed formula. This here is n times n plus 1 over 2. That's the closed formula if you start at 1. Now look at it, 1 times 1 plus 1 is 2, 2 over 2 is 1, so you got 1. If you put 2 in here, you get 2 times 3 over 2, which is 3. So it works. Now how is this very, very closed formula here? How do we adjust it for this sequence? Look here. That is 2, 3, 4, 5, 6. This is 2, 3, 4, 5, 6. Now, isn't that absolute poetry? The growth there and the growth here are the same, which highlights the fact that they should have, in some way, the same general rule that expresses its existence. But what happens? It just goes one step further. So we can say, oh, okay, this has the same growth, which is expressed by that, but it's one further. And that will be our general term. It will be the triangular number transformed 1 unit to the right. If you think about functions, here's the function, it went 1 unit further. Okay, let's see if it works. A1 is equal to 1 times 2 over 2 plus 1. Now that gives us 2. We can see that's 1 plus 1. A2 will be 2 times 3 over 2 plus 1. Okay, the 2's go. 3 plus 1 is indeed 4. Let's just check the third one. A3 is equal to 3 times 4 over 2 plus 1. Now that's 12 over 2, which is 6 plus 1, which is 7. Perfect. So this here is a transformed version of a sequence that we are very familiar with. Another one, if we can quickly, let's look at this. The square number sequence there. The square number sequence is always expressed as that. Okay, that's your general term. The sequence has a closed formula. I'm going to change color. An is equal to n squared. Now we know that this is 1, 4, 9, 16, 25, 36, and that's how it grows. So if you start at 0, 3, 8, 15, 24, 35, can you see, folks, it is one less than what the squared numbers would be. So if I want to now, for this sequence here, create from that a general rule, my general rule will be, oh, wrong number, or wrong function. A n will be the squared numbers, take 1 away. And there, with your squared number sequence transformed, gives you the new sequence. This is what this is saying. It's very important, okay, so that you know sequences, so that you can compare mystery sequences to those sequences that you are familiar with. It's going to take you forever to try and find a pattern here if you don't relate it to that. Then you've got to look at the growth number. Is it constant? Isn't it constant? How do I adjust away? So I want you guys to absolutely in your textbooks make a note of these sequences and make a mental note in your head what their general forms look like. These are all powers of 2. Okay, so they 2 to the n. This is the Fibonacci sequence, and the Fibonacci numbers can be defined recursively. Okay, so if you see that that's the growth, this is how we will express that growth. The previous plus the next, or the previous plus the one before it gives you the next term, and then clearly, obviously, they give you your initial conditions, which is what is needed here. Okay, let's go and let's look at exercise 2. I'm going to try and get rid of this so I have space to write. Exercise 2.1.4. They say the formulas Tn and An. So let's write them down. Tn is equal to n times n plus 1 over t over 2. And An is equal to 2 to the n. Okay, sorry about that. This gives you your powers of 2, and this here gives you your triangular number. Okay, so let's see what they want. They say, use those two, use these two to find closed formulas for those two functions. Okay, so there's a lot coming, so let's go over here. Now, let us in fact stay on that side. So Bn, the sequence Bn is what we're looking for. And how's it built up? It's built of 1, 2, 4, 7, 11, 16, what is it then? 22. So let's see. Growth is 1, 2, 3, 4, 5, 6. Okay, now that's interesting. Okay, so they're asking us to use these two sequences to express this sequence. Okay, so if we look at the very first sequence, Tn over here, let's write it down. If we start at 0, then the sequence starts at 0. Then 1, okay, there we go. Because this is 2 over 2, then the next one will be 2 over 3, so it will give you 3. Then the next one will be 3 times 4, which is 6. Then 4 times 5, which divided by 2 gives 10. And we can see that's our growth sequence. It grows by the 1, 2, 3, 4. Let me just see here. This is not 17. Yeah, this is supposed to be 15. Let me just get rid of that last one. If you do things in your head and you're thinking of other things, that's when silly things like this happens. Okay, so that was a growth of 5, and then the next one would have been 21. It's a triangular number sequence. Okay, so let's see, how is this related to what we've got here? Can we use the two together? I don't know. I've no idea. Let's have a look. So we wish to compare these sequences to the triangular sequences where we start at naught, and then 2 powers of 2 where we also start at naught. So this is 2 to the naught is 1, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. There we go. Okay, so if we look at the sequence that we have, that we're busy working with here, the number sequence, let's see if it relates to our number sequence up there. Well, it looks like naught got added 1, 1 got added 1, 3 got added 1. Then we are missing, but we can see the growth stays the same. Now that is interesting. If the growth stays the same, 6 grew by 1, 10 grew by 1, 15 grew by 1 to 16, 21 grew by 1 to 22. So we can say Bn is, it's a subscript n, n plus 1 over 2. So the growth element is the same as the standard sequence. We will refer to these as, I'm going to introduce a new word, the referent sequence. Okay, the referent sequence. But it's always 1 on. Okay, that's the first one. The second one, number 2, sequence Cn, develops in the following way. 3, 5, 9, what is it, 17, 33. Now let's see. Here we have 2 that we add. There we add 4. Here we all of a sudden add 8. And here there's an addition of 16. Now look at the poetry here, folks. It grows. It grows in multiples of 2, the growth element, starting at 3. So we've got to start at 3 somewhere. Each term in the sequence then is 1 more than the power of, look at this, 3, 2 is 3, 4 is 5, 8 is 9, 16 is 17. The next one would have been 32, which is 33. So it's 1 more. It's always 1 more, the growth, than what we have in the power sequence. Okay, so what is it that we're going to say? Can we say that Cn, where's my pen? Make it red. That Cn is equal to 2 to the power of n plus 1. Let's see. Well, if n starts at 1, we've got 2 plus 1, which is 3. So n is bigger and equal to 1, and n is a natural number. If n is 2, we get 4 plus 1 is 5. If n is 3, we get 8 plus 1, which is 9. 4, 16 plus 1, which is 17. We could have also said that Cn is 2n. Now remember, this here starts at 1. Plus 1, plus another 1. What will happen here? N will be bigger and equal to 0, and will take on natural values. So if n is 0, we get 2 plus 1, which is 3. Then if n is 1, we've got term 2, which makes it 2 to the power of 2, which is 4 plus 1, which gives you 5. So there's 2 ways to talk about this. Okay, we can talk about it as starting at n equal 1 or starting at n equal 2. In fact, we can start anywhere. We could have started at n is bigger than equal to 2, where n is a natural number. Okay, so let's see, what do we have to do? If n is bigger than equal to 2, then Cn is going to be 2 to the n minus 1 plus 1. Let's see. If n is 2, you get 2 minus 1, which is 1. 2 to the 1 is 2 plus 1 is 3. If n is 2, you get 2 minus 1, which is 1. Sorry, yeah, because it goes bigger. If n is 3, you get 3 minus 1, which is 2, and 4 plus 1 gives 5. So the next one, where n is bigger than equal to 3, if we want to define it as that will be C is 2n, and you've got it, minus 2 plus 1. Okay, folks, so that's how this works in terms of finding a general formula for them and finding it using your referent sequences. Let's look at the next page. Let's look at number 3. I'm not going to go through all these examples with you. You can go through them as well, but I think number 3 is quite nice. Number 3 says you're working with a sequence Dn, and Dn is 0, 2, 6, 12, 20, 30, and 42. And it continues in that way. Now remember, our referent sequences is n plus 1 over 2, and let's just write them down. This is 3, then what? It's actually starting at 1. 1. Let's start at 1. Then we get, if n is 2, now look at me, I'm lost. 2, then it's 3. Okay, so that's 2 plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28. And that's how that sequence continues. And our second reference sequence is n squared. So it's 1, 4, 3 squared is 9, 16, 25, 36, and then what, 49. So we need to express what we've got here in terms of that referent sequence. Now, folks, it can be a combination of them. I don't know what we're going to do, but let's have a look. The first thing we can see here is that all our terms are even. Now, if I look at the sequence, there's no, one isn't even or odd. So we've got 6, we've got 10, we've got 28, we've got 4, we've got 16, we've got 36. Okay, that is very interesting, I would say. Okay, now let's see, how do we find it? What happens if for these even numbers over here, we factor out the number 2? If you factor out the number 2 here, in other words, you divide this whole thing by 2. Okay, let's change color. So, sorry, let's change color. Dn, dn over 2 will then be 0, 1, divided by 2, then we get 3. That divided by 2 is 6. That is 10. This is 15. Look at the poetry. And that there, look at this. This is absolutely beautiful. Now we have our triangular sequence. So if I were to write a general rule here for this sequence, it will be the triangular sequence divided by 2 and then again divided by 2. So it will be n plus 1, all of this divided by 4. Now remember, we start at, this is actually, sorry, I'm talking absolute nonsense. The original sequence can then be expressed as the general formula for the triangular number multiplied by 2. Okay, sorry about that stupid mistake. So this is what we've got, and we double it up. So finally, we have n times n minus 1. And folks, that is your rectangular number. Okay, so if n is 1, you get 1. 1 minus 1 is 0. If n is 2, you get 2 times 1. If n is 3, you get 3 times 2, which is 6. If n is 4, here, you get 4 times 3, which is 12. If n is 5, you get 5 times 4, which is 20. And this here is your rectangular number. So remember that as well. When you can form a reference sequence from this rectangular number. Tn is that, and that's rectangular. And remember, what does it look like? It looks like twice the triangular number. Now, folks, just think about this. Those of you that did the geometry course, any quadrilateral regular consists of two triangles that are congruent. So if this is a rectangular number, it's twice the triangular number. It links so beautifully with geometry and with the function work that you've done in the course. Okay, so folks, I'm going to leave the rest of this up to you. The rest of the not the chapter, but up to the end of page 142, where you will complete up to there. Our next section, as you can see, that we will focus on is partial fractions. Partial sums.